The Indian 841 motorcycle stands as one of the most fascinating engineering adaptations of World War II. A machine born from necessity when the United States Army recognized it needed a motorcycle capable of operating in the punishing desert conditions of North Africa. While Harley-Davidson had already secured contracts for military motorcycles, the Army's specifications for a shaft-driven, transversely mounted V-twin engine designed specifically for sand and heat created an opportunity for Indian Motorcycle Company to demonstrate its engineering prowess. Between 1940 and 1942, Indian Springfield, Massachusetts factory would transform itself into a precision war production facility, churning out these specialized machines through a manufacturing process that began thousands of miles away in the ore-rich mountains of Minnesota and ended with crated motorcycles bound for the Sahara. This is the complete story of that journey. From the moment iron ore left the ground to the instant a finished 841 rolled off the assembly line, ready for combat. The story of every Indian 841 began not in Massachusetts, but in the Mesabi Range of northern Minnesota, where some of the richest iron ore deposits in North America had been feeding American industry since the 1890s. Here, in open-pit mines that stretched for miles, giant steam shovels bit into the rust-red earth, extracting ore that contained up to 60% pure iron. The mining operations ran around the clock during wartime, with crews working in shifts that never stopped. The constant rumble of explosives and machinery creating a perpetual thunder across the frozen landscape. Each shovelful of ore represented the potential for steel that would become engine blocks, frames, forks, and transmission housings. The ore traveled by rail in massive hopper cars, hundreds of tons at a time, making the journey south and east toward the steel mills of Pennsylvania and Ohio. During winter, when temperatures plunged below zero, the ore would freeze into solid chunks that required steam thawing before unloading, adding hours to an already complex logistical chain. The trains themselves became targets for efficiency experts who calculated that every hour saved in transit meant more steel reaching factories faster and more motorcycles reaching soldiers who needed them. Alongside the iron ore, another crucial ingredient made its own journey from the coal fields of Appalachia. Metallurgical coal, the specific grade required for steel production, came from deep shaft mines in Pennsylvania and West Virginia, where miners worked in seams sometimes only 3 feet high, lying on their sides to cut coal with picks and pneumatic drills. This coal would be transformed into coke through a process of heating it in the absence of oxygen, driving off impurities and creating the carbon-rich fuel necessary for blast furnaces. The coke ovens themselves were environmental nightmares, belching sulfurous smoke and creating rivers of tar-laden runoff. But they were absolutely essential to steel production. Without coke, there could be no molten iron. And without molten iron, there could be no steel. And without steel, there could be no Indian 841. The synchronization of these supply chains represented a logistical ballet of staggering complexity, with railroad dispatchers coordinating the movement of raw materials from dozens of sources to ensure that steel mills never ran short of either ore or coke. The transformation from ore to steel occurred in the massive integrated mills of Pittsburgh, Youngstown, and Gary, where blast furnaces operated continuously, their internal temperatures reaching nearly 3,000 degrees Fahrenheit. Workers approached these furnaces wearing protective gear that barely seemed adequate for the radiant heat, their faces shielded by thick glass visors that still allowed them to feel the scorching air. The ore, coke, and limestone flux descended into the furnace from the top, while superheated air blasted upward from the bottom, creating a chemical reaction that separated pure iron from the surrounding rock and impurities. The molten iron collected at the bottom of the furnace, glowing with an intense orange-white light that hurt to look at directly. Every few hours, tap crews would drill through the clay plug, sealing the furnace's base, allowing rivers of liquid iron to flow into channels carved in sand, creating formations that resembled a mother pig nursing her young, which gave rise to the term pig iron. This pig iron still contained too much carbon and too many impurities to be useful for motorcycle components. So it moved to the next stage of refinement. The Bessemer converters and open hearth furnaces that transformed pig iron into steel represented some of the most dramatic industrial processes of the era. In the Bessemer process, workers tilted massive pear-shaped vessels and poured in molten pig iron, then forced compressed air through the liquid metal from below. The oxygen in the air combined explosively with the excess carbon in the iron, creating spectacular showers of sparks that shot 30 feet into the air while the vessel itself glowed cherry red. The entire building shook with the force of the reaction, and the roar was so loud that workers communicated through hand signals alone. The process lasted only 15 to 20 minutes, but in that brief time, the carbon content dropped from over 4% to less than 1%, creating true steel with the specific properties needed for engine components and structural frames. Open hearth furnaces offered more precise control, using reflected heat from burning coal gas to melt pig iron and scrap steel together in shallow pools that could be sampled and adjusted by adding carefully measured amounts of manganese, chromium, or nickel to achieve exact specifications. These furnaces operated on 12-hour cycles, and the heat in the building was so intense that workers could only approach the furnace mouth for brief periods before retreating to cool down. The steel destined for Indian Motorcycle arrived at the Springfield factory in several forms, depending on its intended use. Thick billets of high-carbon steel would become transmission gears and crankshafts, while thinner sheets of mild steel provided material for fenders, fuel tanks, and body panels. Specially alloyed steel with added chromium or molybdenum arrived as round bar stock for connecting rods and valve stems, materials that needed to withstand enormous stresses without failing. The receiving department at Indian's factory operated with military precision, checking each shipment against specifications and routing materials to the appropriate production departments. During peak production in 1941, the factory consumed over 50 tons of steel per week, all of it requiring careful inventory management to ensure that production lines never stopped for lack of material. The raw steel often arrived with a coating of rust-preventive oil and mill scale, the dark, oxidized layer that formed during cooling, which would need removal before machining could begin. In the forge shop, bar stock transformed into crankshafts through a process of controlled violence that had remained essentially unchanged for centuries. Workers heated steel billets in gas-fired furnaces until they glowed bright orange, indicating they had reached approximately 2,000 degrees and had become plastic enough to shape. Using massive drop hammers and hydraulic presses, they forced the hot steel into dies that formed the basic crankshaft shape, complete with counterweights and journal surfaces. Each blow of the hammer rang through the building like a church bell, and the floor itself trembled with the impact. The forging process aligned the grain structure of the steel, making it far stronger than if it had been cast or machined from solid stock. After forging, the rough crankshafts moved to heat treatment, where they were reheated to precise temperatures and then quenched in oil baths, creating a hard outer surface while maintaining a tough, resilient core. The heat treaters worked from charts that specified exact temperatures and quenching times for each component, knowing that mistakes could result in parts that were either too brittle and prone to cracking or too soft and subject to premature wear. The machine shop occupied the largest floor space in the Indian factory, a vast room filled with row upon row of lathes, milling machines, drill presses, and grinding equipment. Here, rough forgings and castings became precision components through the systematic removal of metal, cut by cut, until they matched engineering drawings accurate to within a few thousandths of an inch. The crankshafts from the forge shop arrived here for finish machining, where skilled operators mounted them in lathes and turned the journal surfaces to exact diameters, creating the mirror-smooth finish necessary for proper bearing operation. The smell of cutting oil hung heavy in the air, mixing with the metallic scent of fresh-cut steel and the ozone tang of electric motors. Each lathe operator worked to a production quota, typically finishing 8 to 10 crankshafts per shift. But quality took precedence over speed, and inspectors regularly pulled random samples for detailed measurement. A crankshaft that passed inspection might operate flawlessly for thousands of miles, while one that deviated even slightly from specifications could fail catastrophically, potentially costing a soldier his life. Big cylinder barrels required a completely different manufacturing approach, one that combined casting expertise with precision boring techniques. The foundry workers poured molten aluminum alloy into sand molds, creating rough cylinder castings with thick walls and excess material. Aluminum offered significant weight savings compared to cast iron, crucial for a motorcycle that needed to operate in deep sand where every pound mattered. The molten aluminum, heated to 1300 degrees in electric furnaces, had to be poured quickly before it began to solidify. And the foundryman's skill lay in knowing exactly when the metal had reached the perfect temperature and fluidity. After casting, and the cylinders moved to boring machines equipped with single-point cutting tools that gradually enlarged the interior diameter while maintaining perfect roundness and straightness. The boring process generated long ribbons of aluminum that curled away from the cutting tool, and the machines required constant coolant flow to prevent heat buildup that could distort the thin cylinder walls. Final honing used abrasive stones to create the crosshatch pattern necessary for proper piston ring sealing, a process that took nearly an hour per cylinder and required constant dimensional checking with precision gauge pins. The distinctive transverse V-twin engine design of the 841 required the two cylinders to sit at 90 degrees to each other, with the crankshaft running fore and aft in the frame rather than across the machine as in traditional Indian designs. This configuration demanded a completely redesigned crankcase, cast in aluminum to save weight, but requiring enormous strength to handle the torsional loads of the engine and the shock loads transmitted through the shaft drive system. The pattern shop had created wooden masters for the crankcase molds, each piece carefully shaped and sanded until it precisely matched the engineering drawings. These masters went to the foundry where molding sand, mixed with clay binders and packed around the patterns, created the negative space into which molten aluminum would flow. The pouring operation demanded perfect timing, with crews ladling metal from crucibles and filling the molds in smooth, continuous motions that prevented air entrapment or premature solidification. Any hesitation or interruption in the pour could create weak spots or voids in the casting, flaws that might not become apparent until the engine experienced the stresses of combat operation. In the assembly department, the 841 began to take shape as individual components came together in a carefully choreographed sequence that transformed bins of parts into functioning motorcycles. The assembly line moved at a deliberate pace, with each station responsible for specific tasks and each worker trained to perform their operations in precise order. The process began with the frame, a welded steel structure that provided the backbone for everything else. Fixtures held the frame tubes in perfect alignment, while welders ran beads along each joint, and creating bonds stronger than the base metal itself. The welding area glowed with the blue-white light of arc welders, and the sharp crack and sizzle of electricity turning into heat filled the air. Welders wore heavy leather aprons and dark-tinted helmets, their faces hidden behind the protective glass that filtered out the harmful ultraviolet radiation. Each weld required careful inspection for cracks, porosity, or incomplete penetration, defects that could lead to catastrophic frame failure. The engine assembly began on separate benches, where specialized mechanics built up each component group before final installation. The crankcase halves, machined to precise tolerances, came together around the crankshaft with carefully measured gasket materials sealing the joint. Mechanics torqued each bolt to exact specifications using calibrated wrenches, knowing that over-tightening could strip threads or distort castings, while under-tightening could allow oil leaks or joint separation. The transmission gears, each one cut on specialized gear hobbing machines and individually inspected for tooth profile and spacing, slid onto shafts inside the gearbox housing. The shaft drive system, the 841's most distinctive feature, connected the transmission output to the rear wheel through a sealed housing containing beveled gears and constant velocity joints. This system eliminated the chain that every other military motorcycle used, providing protection from sand and dust that could quickly destroy exposed chain drives in desert conditions. The engineering elegance of the shaft drive came at a cost in complexity and precision manufacturing, with each component requiring exact dimensions and perfect heat treatment to prevent premature failure. The fuel system assembly brought together components from multiple suppliers, all of which had to work in perfect harmony despite having been manufactured in different facilities. The carburetor arrived from a specialized manufacturer in Detroit, its tiny jets and passages calibrated to deliver the precise air-fuel mixture the engine needed. The fuel tank, formed from stamped steel sheets and welded along the seams, came from the sheet metal department after having been cleaned, primed, and painted in the distinctive olive drab that marked all military equipment. Gunner workers installed rubber fuel lines that had to resist both gasoline's solvent properties and the heat generated by the engine, securing each connection with screw clamps that provided leak-proof seals. The fuel petcock, a simple valve that controlled fuel flow from the tank to the carburetor, incorporated a sediment bowl that trapped dirt and water before they could reach the engine, a critical feature in desert environments where dust infiltrated everything. The electrical system required equally careful assembly, with components that had to function reliably in conditions ranging from freezing European winters to scorching North African summers. The magneto, which generated electricity through rotating magnets inside coils of wire, arrived as a complete unit from the Bosch factory in Springfield, Illinois, its timing already set to precise specifications. Workers bolted it to the engine case in a position that allowed the drive gear to mesh perfectly with the crankshaft gear, then checked timing with a specialized indicator that measured exactly when the spark would fire. The wiring harness, assembled on a separate bench using color-coded cloth-covered wires, included connections for the headlight, tail light, horn, and ignition kill switch. Each wire terminated in either a bullet connector or ring terminal, and workers had to match colors carefully to avoid misconnections that could cause electrical fires or component failures. The headlight assembly incorporated a blackout feature that reduced the light output to a narrow slit barely visible from ground level, allowing night riding without giving away positions to enemy aircraft or observers. The front fork assembly demonstrated the engineering compromises necessary to create a motorcycle that could handle both on-road and off-road conditions while maintaining soldiers' serviceable simplicity. Indian's traditional leading link front suspension gave way to a conventional telescopic fork design that provided more travel and better damping over rough terrain. The fork tubes, manufactured from seamless steel tubing, slid through bronze bushings in the triple clamps, guided by internal coil springs that compressed and rebounded as the wheel encountered bumps. Each fork leg required assembly in a specific sequence, beginning with the installation of the spring and damper rod, followed by the careful addition of measured amounts of hydraulic oil that provided damping action. Workers then compressed the fork to its minimum length, slid the upper tube over the lower assembly, and tightened a cap that sealed the system and maintained internal pressure. The entire assembly then mounted to the frame through the steering head, where tapered roller bearings allowed smooth steering while handling the considerable side loads generated by rough terrain. The rear suspension utilized a plunger system that was innovative for its time, with the rear wheel assembly able to move up and down against spring pressure while maintaining drive shaft alignment. This design required sophisticated machining of the swing arm housing, which had to accommodate both vertical movement and rotational forces while maintaining oil sealing around the drive shaft. The springs themselves, wound from high carbon steel wire and heat treated to prevent sagging under load, provided approximately 3 inches of travel, sufficient to smooth out moderate bumps while maintaining enough stiffness to prevent the chassis from wallowing on high-speed runs. Adjustable shock absorbers, filled with hydraulic fluid and incorporating internal valving to control rebound speed, bolted between the frame and the swing arm, giving riders the ability to tailor suspension response to load conditions and terrain type. The wheel and tire assembly represented one of the few components where Indian relied entirely on outside suppliers, but integration into the motorcycle still required careful attention to detail. The wire spoke wheels arrived from a supplier in Indiana, their steel rims already laced to hardened steel hubs through dozens of individually tensioned spokes. Workers mounted the tires, manufactured by Goodyear specifically for military use, using tire irons and carefully avoiding pinching the inner tubes during installation. The military specification tires featured aggressive tread patterns designed to provide traction in sand, mud, and loose gravel, with reinforced sidewalls that resisted punctures from thorns and sharp rocks. After mounting, workers inflated the tires to specified pressures and then submerged the entire assembly in water tanks, each watching for the telltale streams of bubbles that would indicate leaks in the tubes or imperfect seals between tire and rim. The final assembly stations brought all the major sub-assemblies together, transforming collections of components into complete motorcycles. Workers lowered engines into frames, aligning mounting points and threading bolts through carefully positioned holes. The exhaust system, fabricated from steel tubing and equipped with military specification mufflers that reduced noise while maintaining adequate power output, bolted to the cylinder heads with gaskets that had to seal perfectly despite repeated heating and cooling cycles. The seat, a minimalist affair consisting of a steel pan with a thin foam cushion covered in water-resistant vinyl, mounted to a spring-loaded post that provided a modicum of suspension travel. Though riders would quickly learn that the 841 prioritized function over comfort. Control cables, routed through guides welded to the frame, connected handlebars to carburetor, clutch, and transmission, each cable requiring precise length and tension adjustments to ensure smooth operation without binding or excessive slack. The testing department represented the final quality control checkpoint before motorcycles could be crated for shipment. Each completed 841 received a comprehensive inspection that began with static checks of all major systems and ended with an actual test ride on the factory's outdoor course. Technicians checked fluid levels, verified proper clutch operation, tested all lights and electrical systems, and examined every visible bolt and connection for proper installation. The test ride, conducted on a course that included pavement, gravel, and a sand pit specifically constructed to simulate desert conditions, allowed riders to evaluate engine performance, transmission shifting, brake function, and handling characteristics. Any motorcycle that exhibited problems during testing returned to the assembly line for correction, with supervisors investigating whether the issue stemmed from defective parts, improper assembly, or inadequate design. During the peak production period, the test department evaluated nearly 50 motorcycles per day, maintaining rejection rates below 2% through rigorous quality standards and continuous feedback to production workers. The packaging and crating operation transformed tested motorcycles into shipping-ready units that could withstand the rigors of transcontinental rail travel, meets ocean transport, and final delivery to forward areas. Workers drained fluids to prevent leakage during transport, removed batteries to avoid corrosion damage, and coated all bare metal surfaces with a thick layer of Cosmoline, a waxy rust preventive that could be washed off with hot water and solvent at the destination. The motorcycles then entered specially constructed wooden crates, built from rough sawn lumber and reinforced with steel strapping at critical points. Workers inserted wooden blocking around the wheels and frame to prevent movement during transport, and included cans of engine oil, spare parts kits, and technical manuals inside each crate. The completed crates, weighing over 400 pounds each, received stenciled markings indicating contents, destination, Newark, and handling instructions before being loaded onto railroad cars for the journey to East Coast ports. The logistics of moving finished motorcycles from Springfield to combat zones involved a coordination effort that spanned multiple continents and required cooperation between civilian and military authorities. Trains carried the crated motorcycles to ports in New York, Boston, and Philadelphia, where they joined convoys assembling for the dangerous Atlantic crossing. During the height of the U-boat threat, cargo ships traveled in groups protected by destroyer escorts, zigzagging across the ocean to avoid torpedo attacks, while hoping that their cargoes of war materials would reach British or North African ports intact. Ships that survived the crossing unloaded at docks where military logistics personnel took charge, sorting crates according to priority and destination. The 841 motorcycles, originally intended for desert warfare in North Africa, found their actual operational deployment limited when the Army realized that Jeeps could perform most reconnaissance roles more effectively. Many of the 841s ended up in training roles or in the hands of military police units. Their sophisticated engineering and expensive production ultimately underutilized in a war that demanded quantity over specialized capability. The Indian 841 production run ended in 1942 after fewer than 1,000 units had been manufactured. A short production life that reflected both changing military requirements and the immense expense of producing such a specialized machine. The factory that had geared up to manufacture these motorcycles quickly pivoted to other military contracts, including increased production of the more conventional Chief models and manufacturing of components for other war materials. The tooling, patterns, and fixtures created specifically for the 841 were packed away into storage, representing a significant investment in engineering and manufacturing capability that had yielded only a brief production run. Yet the 841 represented something more than just another failed military contract. It demonstrated American industry's ability to rapidly develop and manufacture sophisticated machinery to meet specific military requirements, even when those requirements proved more theoretical than practical. The complete manufacturing chain, from Minnesota iron mines to the final test rides in Springfield, showcased the interconnected nature of American war production, where thousands of workers in dozens of facilities contributed their specialized skills to creating complex machines designed for a conflict half a world away. Today, surviving examples of the Indian 841 are prized by collectors not just for their rarity, but for their representation of a moment when American engineering ingenuity and industrial capability combined to create a motorcycle unlike any other. A machine that pushed the boundaries of design, even if it never quite found its intended battlefield role.